Okay, you guys, here's what we need to try to cover today. Here are the syllabus references in IB Physics for simple harmonic motion. You should be able to define simple harmonic motion and state the defining equation as acceleration equals negative omega squared times x. We'll talk about that a little bit, but recognize that this is the equation that defines when you get simple harmonic motion. If the acceleration of an object is directly proportional to the displacement of that object and in the opposite direction. Those are the three critical things of that equation. Omega we'll talk about in a little bit. It's really just a constant for all intents and purposes right now. The idea is if you move an object away from equilibrium and it accelerates in the opposite direction of the way it was moved, and the amount of acceleration is proportional to how far you've moved it, the result is simple harmonic motion. Okay? That's why we call it the defining equation for simple harmonic motion. Okay, we should be able to solve problems using the defining equation. We should apply the equations which are solutions to the defining equation and be able to solve problems, both graphically and by calculation, for acceleration, velocity, and displacement during simple harmonic motion. So that's our goal today. Okay. One of the things I want to start with today is looking at the relationship between uniform circular motion and simple harmonic motion. Uniform circular motion, you guys, we studied last semester, so it's been a little while. But let's revisit it for a second. When I say uniform circular motion, what has to be uniform?
The circle.
What about the circle?
The motion.
The radius. Okay, so we have a constant radius. So we have a constant radius, and there's something else that's constant.
Velocity.
Constant velocity and constant acceleration. The acceleration is always centripetal, and the velocity stays, well, technically it's the speed that stays the same, right? Because yeah, well, it's always towards the center, so that we can define. Okay, the velocity is always changing, but the speed is constant. Okay, so in uniform circular motion, you have an object going around in a circle of constant radius with a constant speed. Great. There's a relationship between uniform circular motion and simple harmonic motion. And here's basically what it is. It says it here. This may not make much sense verbally, but I'll show you a picture. But if you look at an object in uniform circular motion and you look at it from a diameter, what you will see is simple harmonic motion. And this is what that means. Imagine on this table, this little red dot is undergoing uniform circular motion in the counterclockwise direction, okay? If instead of looking at it from above, if I were to go down and look at it from the side, okay, like this observer here is watching this little red ball go around in a circle from the side, the motion that I would observe is simple harmonic motion. It would appear to go back and forth, back and forth, back and forth, just like the mass on the spring is going back and forth, okay? And it turns out the reason this is useful is because the mathematics of circular motion can lead us to the equations for simple harmonic motion, all right? So let's just kind of look at it for just 1 second. Notice that right here, it has its velocity at that instant is v sub 0, okay? Because remember, the velocity in circular motion is tangential to the circle. The x component of its velocity, the x component of that vector is right here. And if you kind of imagine that what you're seeing, if you're this observer, all you're seeing is the motion in the x direction. You can't see motion in the y direction because it's coming towards you and away from you. So you're just seeing it go back and forth. Look at what happens. When the object's right here, how much velocity does it have in the x direction? What's that? None, right? It's only moving in the y direction. So what you would observe is no velocity. And think about simple harmonic motion. When it gets to the extreme, that's the point where the velocity stops, okay? When the little red object comes around to here, where you would observe it right here from the side, now notice that its velocity is maximum, just like simple harmonic motion. The velocity is maximum when it reaches equilibrium, okay? And then back to here, you would see no velocity, and so on and so on and so on. So the relationship is very, very similar. Let's look at acceleration for a second. Notice this is, in simple harmonic motion, where is the acceleration directed? Towards the center. It's always centripetal, towards the center. So when the object's right here, its acceleration is centripetal. Well, notice that that would be maximum acceleration, right? And then right here, you would see no acceleration. And then back to here, you'd see maximum acceleration back towards equilibrium again. So watching circular motion from the side is exactly the same as simple harmonic motion. okay? And we can do some math. I'm not going to do it right now, but notice that we can do some things. If I wanted to find the velocity of an object in simple harmonic motion at any given instant, if I wanted to see the velocity of that mass at any given instant, it would be the same as finding this component of the velocity of an object in circular motion at that instant, okay? And that's where some of these equations get derived from, because there's relationships here between the radius of the circle and the angle and what's happening in the x direction. Does that make sense somewhat? Okay. Let's talk about this concept, omega. Omega is meant to represent angular frequency or angular velocity in some textbooks. And basically what this is, it's measuring, it makes more sense in terms of circular motion. You think of something going around in a circle. Use a different color. If you think of something going around in a circle, I can measure its velocity at any given instant that we've talked about, right, with it being tangential to the circle, but I can also measure its velocity in terms of the size of the angle that it creates in a certain time period. Rather than distance versus time, I can look at it as an angle versus time. You with me? That would be angular velocity or angular frequency, okay? I could say its angular velocity is 90 degrees per second, or 180 degrees per second, or 360 degrees per second. You with me? Okay. But the problem is we don't use degrees. We use radians, okay? So that's the only difference. So how many radians are in a complete circle? 2 pi. Great. That's where this 2 pi comes from, okay? Because that's one complete circle worth of radians, and if I multiply that by the frequency, okay, the number of oscillations per second, or the number of circles per second, I get the angular frequency, or the angular velocity. That is what omega is, okay? In your data booklet, here's the equation for omega. It says omega equals 2 pi over the period. Remember that frequency and period are inversely related? Okay? Frequency equals 1 over period. Period equals 1 over frequency. The unit for angular frequency, the unit for omega, is radians per second. And again, there's 2 pi radians in a complete circle. So now let's look at our definition of simple harmonic motion once again. Simple harmonic motion is a type of motion that occurs when the acceleration of an object is proportional to its displacement from equilibrium and is directed in the opposite direction, or directed back towards equilibrium. So whenever you have a situation where the more you move something away from equilibrium, the greater the force gets, and that force is directed back towards equilibrium, you will get simple harmonic motion. So the mass on the spring, the more I pull down on the spring, the more it pulls back. When I release it, the result is simple harmonic motion. If I have a bowl with a marble in it, and I pull it up to the side, there's going to be a force trying to pull it back to equilibrium, and it will oscillate back and forth around that. A pendulum, another classic example. From that, you get this equation, A equals negative omega squared x. That is the defining equation for simple harmonic motion. It's related to this equation, F equals negative kx. Where did that come from? Force of a spring. And what law was that? Hooke's law. Excellent. So this is Hooke's law, the force that a spring or an elastic system will generate. Take a look here. So I have this, and I have Newton's second law, F equals ma. Right? Okay? But F equals negative kx when I talk about a spring. So I can say that ma equals negative kx. So A equals negative k over m times x. It turns out this quantity, the spring constant divided by the mass, is the same thing as omega squared. Okay. I don't know that you'll actually have to do that math, like ever have a problem where you have to do that kind of a calculation, but that's the relationship. This idea of omega squared being a constant, well, it's the spring constant divided by the mass that's on that. Okay. Negative k over m times x. That equals acceleration. Omega squared is this k over m. Yeah. So we talked about this a little bit before, but remember that simple harmonic motion is related to sine, cosine functions. It's related to these wave functions. So this is kind of the relationship between SHM and waves. Remember that if I have a mass on a spring like this and I were to attach a pin to it, and I were to stick a piece of paper behind it so that pen was touching it, at first, if I didn't do anything, it would just make a line up and down. But if I started moving, I would create a wave, like this picture, right? Okay? And this is just a graph of displacement versus time. This is the displacement of the mass as time progresses, and we've marked time on the time axis in relation to the period, right? So one complete cycle is the period, then you've got half and quarter period. What I'd like you guys to do with your friends and your family is to, from this graph, draw the corresponding VT graph and AT graph, the velocity of the object and the acceleration of the object. This is a DT graph. This is displacement versus time, okay? So when I started my stopwatch, it was at maximum displacement. And then this is the amplitude, exactly. Which, by the way, in IB terms, again, this is not A, this is X sub 0, okay? So from this, go ahead and draw the VT graph that goes with it and the acceleration time graph that goes with it, all right? All right, guys, let's take a look, see what we have, okay? So here's our displacement time graph. I already showed you that. It's that one right there. The corresponding VT graph, you can do this a couple different ways, okay? You might remember that a VT graph is the slope of a DT graph. So one way to think about it is purely mathematically. If I can just make a graph of the slope of this graph, I'll have it. Or you can think about it conceptually in terms of simple harmonic motion. When the mass is at its amplitude, when it's farthest from equilibrium, what's its velocity? 0. And when it's at equilibrium, what's its velocity? Maximum. So I know that here it's got to be 0, here it's got to be maximum, here it's got to be 0, here it's got to be maximum. Yeah? So you can look at it that way too. Ultimately, however you do it, hopefully it comes out something like that. One of the critical things is to recognize that here its slope is negative, so it's going to be maximum in the negative direction, okay? And here the slope is positive, so that gives me a maximum in the positive direction. All right? Not always, but generally. You can do it either way. But generally we say up is positive and down is negative. Okay? Now the acceleration time graph, same thing. The acceleration time graph will be the slope of the VT graph, or you can think about it conceptually. Okay? When the object is at the farthest from equilibrium, is the acceleration 0 or maximum? Maximum. Okay? When the object is at equilibrium, what's our definition of equilibrium? No acceleration. So I know that it's going to be maximum here, 0 here, maximum here, 0 here. However, what's true about the direction of the acceleration? It's opposite of the displacement. So you'll have a graph that looks just like displacement, but flipped. Okay? Okay, let's take a look at this mathematically too. What do we have here? What kind of a curve do we have for our DT graph? Is it? No? Cosine. Okay. That's a cosine curve. Okay. What about our VT? Negative sine. And what about our AT? Now, a couple of things I want you to recognize. The reason we have this as a cosine, negative sine, and a negative cosine, the only reason it's that way is because of when we decided to start our stopwatch. I chose in this particular, I didn't, but these people did, to start timing when the displacement was at a maximum. But I could just as easily have started timing, I could have done it any time, but another good place to start timing is when the displacement is at equilibrium. That's another possibility. And the only thing that would change is where my y-axis is and where my curve starts. So I could start here, but a lot of times we actually talk about starting here. And now notice that if I started timing here, my displacement is a sine wave, and my velocity then is a cosine, okay? So that's all that changes when you determine where you're going to start your stopwatch. Okay? The other thing,
In most cases, will we be presenting?
well, here's the trick. I'm going to show you the equations that we work with these problems with, and you have to determine where the time was started in order to know which equations to use. And all it does is either sine or cosine depending on where you start. Okay? The other thing that you don't necessarily need right now, but I want to put in your head somewhere, is this. Let's see, this is negative cos. Okay. To get from a dt to a vt graph, what do we use? The slope. Okay, the slope of a dt graph tells us the vt. Same is true here. You with me so far? When you take calculus, which many of you will be taking soon if you've not taken it already, a major portion of what calculus is about is finding the slope of curved functions, okay? And there's a name for it. It's called taking the derivative, or it's also called differential calculus. When you take the derivative of a function in calculus, you basically get a new function that will tell you the slope of it. So if I were to take the derivative of a cosine curve, guess what I would get? A negative sine curve. And if I take the derivative of a negative sine curve, I get a negative cosine curve, okay? Just remember that next year when Jamie's teaching you some calculus and say, I remember this, simple harmonic motion, it's all connected, okay? All right. Now let's look at the equations. It turns out if I take that defining equation, a equals negative omega squared times x, and I do some calculus to it, I get some solutions. I get some ways to solve for the position of an object that's in simple harmonic motion and the velocity of the object that's in simple harmonic motion at some time t later, right? If I know certain things, I can figure out how fast it's moving and where it's going to be at some time later. And the equations look kind of ugly and kind of messy, but they're really not so bad when we break them down. Here are the two equations, okay? The position of an object that's oscillating in simple harmonic motion, okay, is equal to, this is the amplitude, x sub 0 is the amplitude, here's the cosine, here's omega, that angular frequency that we talked about, and this is t, some time period later, plus, you know, amplitude sine omega t. So this allows me to find the position at some time t later, and I have the similar equation for the velocity. Now these are kind of ugly because you got sine and cosine in there, but there's a great thing about these equations that makes them a lot easier. When I started my stopwatch, and this thing was at maximum displacement, what kind of graph did I get for dt? Cosine, right? It turns out if I start my stopwatch at maximum displacement, this goes away. Yeah, okay? And this goes away because remember my VT graph was a negative sign, right? Guys remember that? The graphs we were just looking at? If, however, I start my stopwatch so that it's at equilibrium when I started timing, these go away, and these become my equations. Okay? It depends on where you start, which equations you use. Okay? So if I start, and I'll show you this in a better, I'll organize this better for you in just a second. Okay? So I just want you to see. If you start timing when the displacement is at 0, these are the equations you use. If you start it at maximum, these are the ones you use. Yes. These are known as boundary conditions, okay? The boundary conditions that help you solve this problem. So if the position of the object is its maximum when I start my stopwatch, when t equals 0, then these are the equations I use. If the position is equilibrium, or x equals 0 at t, when I start my stopwatch, when t equals 0, then those are the equations I use. So that's how it simplifies. And in your data booklet, if you take a look at it, you'll see how they write this out. So notice that when I start my stopwatch, if my object is at its greatest displacement, these are the two equations I use. This tells me the displacement. This tells me the velocity at some time t later. Okay? Anything sub-0 is maximum. Okay? V sub-0 is maximum velocity. X sub-0 is maximum displacement. Okay? A sub-0 would be maximum acceleration. If, however, when I start my stopwatch, the displacement is 0, it's at equilibrium, these are the two equations I use to find position and to find velocity. Okay? They allow me to find the position and the velocity at some time t later, as long as I started timing when it was at equilibrium. Okay? And if you think about it, it's really those graphs we've been drawing. Remember, the graphs we were drawing we got a cosine curve and a negative sine curve for displacement and velocity. If, however, I chose to have started my stopwatch when it was at equilibrium, I'd get a sine curve for displacement, and I'd get a cosine curve for velocity.
Are we ever going to get an idea?
The bottom equation is useful in all times with simple harmonic motion, but notice what it tells us. It allows us to calculate the velocity of an object that's in simple harmonic motion. Remember, its velocity is always changing, but we can find its velocity at a certain point, not at some time later, but when it's at some location in its motion, okay? So these upper equations deal with time. This lower equation deals with location and not time. So if I want to know how fast it's moving when it's somewhere in its simple harmonic motion, this is the equation I can use. And from that, there's a nice thing. When is it, at what point in its motion is its velocity the greatest? At equilibrium. So notice, and at equilibrium is when x equals 0, right? So if I want to find the maximum velocity, it happens when this equals 0, and this becomes omega times the square root of amplitude squared, which is just that, okay? So one thing I can do with this equation is I can find the maximum velocity very easily if I know omega, the angular frequency, and I know the amplitude. This one will tell me the maximum velocity for that object. Now, you guys remember when we talked about simple harmonic motion last time, and we said that dealing with velocity and acceleration is really complicated because it's always changing. So it's easier to deal with energy in simple harmonic motion, right? Remember that? Anyone? Bueller? Great. Okay. So, and remember, as this thing's oscillating, okay, what kind of energy does it have at its maximum displacement? Potential. And that turns into kinetic. And it goes back and forth, back and forth, back and forth. Great. It turns into kinetic. Here are the equations. Once we now know omega, once we know the angular frequency, we can use these equations to find the kinetic energy of the object at any location in its motion. That's what this first equation tells us, the kinetic energy at any point when it's moving. Now, when is the kinetic energy the maximum again? Wait, what location? Equilibrium. So notice that if I want to find the maximum kinetic energy, this goes away because x equals 0, right? And so it just becomes this equation, which that's pretty easy. Great. And therefore, that must be what the total energy is, because when it's at equilibrium, all its energy is kinetic. And then it all becomes potential and back and forth, back and forth. At any, right now we're looking at any place in its motion. Mass. Mass. Okay? So the second one being maximum kinetic energy? Yeah. One thing I want you to notice about this last equation, you will get questions about this. So perk up your ears for a second because you'll see questions about this. The total energy in an oscillating system, is proportional to the amplitude squared. That's important to know, okay? Exactly. If a wave is twice as tall, it carries 4 times the energy. Okay? If it's 3 times as tall, it carries 9 times the energy. For a tsunami, it carries huge amount of energy. So the energy carried in oscillating motion is not directly proportional to the amplitude. It's directly proportional to the amplitude squared. That's kind of an important thing to know. Tati. Okay. The last thing I want to talk about is this concept of damping, you guys. And here's the deal. We've been talking about simple harmonic motion as if an oscillating object will continue to oscillate forever without anything changing. And we know that that doesn't happen. We know that there is energy that is lost to friction and other things. But in certain cases, like my mass on the spring right here, it'll oscillate for quite some time before it stops because it's not losing energy that rapidly. The idea of damping, when we say damped harmonic motion or damped motion, is that the simple harmonic motion decreases over time, okay? And that's naturally going to occur in any system. Sometimes, however, we have certain things that oscillate that we want to damp. So we talk about particularly like in cars and in motorcycles and in shock-absorbing systems, we want that motion to be damped. And the idea is this. Something that is critically damped doesn't oscillate at all. When it's been displaced, it gets back to equilibrium as quickly as possible. And this is kind of how you want the shock absorbers in your car to be. You're driving down the road, you hit a bump. That shock absorber compresses, and you want it to get back to equilibrium without bouncing a whole bunch. Okay, you don't want it to oscillate a whole bunch, because otherwise you're like jiggling down the highway, right? If something is overdamped, it takes too long to get back to equilibrium, and that's this curve here. Okay, that's a shock absorber that compresses and doesn't rebound fast enough, so your car hits it, and then you're stuck for a little while before it gets back to equilibrium, and you hit another bump, and you're like, oh, this is horrible. Something that is underdamped, this is when your shock absorbers completely wear out. You go over a bump, and it displaces it, and rather than going right back to equilibrium, it goes the other way, and then the other way, and then the other way, and it takes a while. It oscillates back and forth before getting to equilibrium. That is underdamped, and that's like when your shocks of your car are completely blown out, and you hit a bump, and your car's going along down the highway, and it's not getting back to equilibrium. Okay. Okay, here's an IB problem. This is a good one. Give it a try. 5 questions. All right? 5 questions. 1, 2, 3, 4, 5. Yeah. 25 what? Centimeters per second. Because if you used 8, it would have been centimeters. You could convert it into meters. That'd be fine. But you'd use 0.08 instead. And it depends. It depends on what you're looking for and what you're using. If you have an equation that has a constant in it, then yes, you need to be in meters and seconds in order for that constant to work at that value. Okay. But in an equation like this where, there is no constant, it's okay to keep it in centimeters. You'll get the same answer because it should be 0.25 meters per second. Doesn't change anything. Yeah, exactly. Okay, now number 4 was giving some people a hard time a little bit. What did we do? There's 2 different ways you can go about number 4. 2 different ways. What's one way someone did it? Look.
Here's the equation. Okay, so you know that they started the timer when displacement's at maximum.
Okay, so the timing was started when the displacement was maximum. So that gives you the boundary conditions for your equations. Great.
Exactly. So you could do V. This is 4.
Yeah.
You do V equals negative 25 centimeters per second. That would be
okay. Okay.
Times sine 3.14 times 1.3.
So it's omega t, right? Great. All right. And omega is pi, right?
Yep.
T is 1.3 seconds.
Yep.
And when you do it that way, what do you get for an answer?
You get 20.
Okay, so 20 centimeters per second or 0.2 meters per second, right? Okay? Another way to do this if you wanted to, was to say 1.3 seconds is right here. My displacement at that time is about 5, negative 5. And then you could use this equation. What was this equation? Help me out here. Negative omega square root x naught squared minus x squared, something like that?
X squared minus.
What's that? Right. Okay. So you could do that using now negative 5 for x and 8 for x naught, and that should give you about the same answer. And it is plus or minus, thank you. And that's just because the velocity changes direction. Okay? So everybody good? Pretty good? All right. So here's where we started. So now we know how to define simple harmonic motion, solve problems using that equation. And these equations is what we just practiced, applying that graphically and everything else.